Start recording. All right, folks, here we are. We're back on track, getting ready. We're going to do our thing. We are in chapter 13. This is going to be a repeat, just in case I had some people gone last week, the week we had school. So I'm going to repeat this lecture, repeat the homework. For some of you, you'll be slightly ahead of the game. We just want to make sure everybody's on the same page. So chapter 13, this is our gases chapter. Cool stuff, describing properties of gases. Let's have fun. Objectives. Objective 1, you need to be able to describe atmospheric pressure and explain how barometers work. I have that barometer in the front of the room. Eventually, I'm going to teach you how to use it. Identify the units of pressure. Pressure has multiple units. We'll use SI units, and we'll use units as for conversion factors. We'll do lots of practice with converting from one unit of pressure to another. You need to be able to explain how the pressure and the volume of a gas are related. Again, this is direct proportionality or inversely related, those kind of things. So just make sure we kind of understand those. We'll talk about them. You need to be able to perform calculations involving Boyle's law. We talked about that. You guys did a little bit of practice for me last week. You need to be able to describe the concept of absolute zero. Remember, I taught you that word extrapolate the data. We need to explain how volume and temperature of a gas are related. Again, we talked about that. I showed you the little fire piston thing. We talked about some fun stuff there. Perform calculations involving Charles' law. Explain how the volume and number of moles of a gas are related. You need to be able to perform calculations involving Avogadro's law. So, well, if you need the objectives, you pause the screen, you copy them down. This is going to be quick. Pressure, sweet. Measuring pressure. We use a barometer. This is an instrument that was invented a long time ago by this guy named Evangelista Torricelli. It measures atmospheric pressure. It was invented in about 1643. One of the units of pressure we'll talk about is a torr, again named after Evangelista Torricelli. Barometers work like this. We have this vacuum, this empty chamber. We fill it completely with mercury. And then we invert it into a disk of mercury, an open vat of mercury. And then this will drop a little bit, but again, this is a vacuum. There was nothing, no air in there. Everything was filled with mercury. And it drops just a little bit because now we've got the force of the atmosphere holding up this column of mercury. And what do we know right now? If that column is not moving, well, then that means the force of the atmosphere pushing down must be equal to the weight of the mercury column in here. And so we can measure, barometers measure in millimeters of mercury. Standard atmospheric pressure is about 760 millimeters of mercury. Changing weather conditions, we always hear that it's a high pressure system, it's a low pressure system. What does that mean? Well, if we look right here, we've got a high pressure, a high atmospheric pressure, 760 millimeters of mercury. We expect to go play some frisbee golf, hang out in the sunshine in the park. And then we have a low pressure system, about 740 millimeters of mercury, rainy, cloudy weather. Yeah, not really want to go outside. Okay, changing altitude will also change atmospheric pressure. We have higher atmospheric pressure at lower elevation. As we climb higher, there is less atmosphere above our heads weighting us down than there is somewhere close to sea level. Elevation changes and whatnot. Units of pressure, again, I had you guys record these last week. One standard atmosphere is equal to 1 atm, is equal to 760 millimeters of mercury, is equal to 760 torr, is equal to, I'm going too fast, 101,325 Pascal. And Pascal is kind of our unit of measure. We'll hang out with atmospheres in Pascal. So we'll read the barometer in millimeters of mercury, then we'll probably convert to atmospheres or Pascal for math. A manometer. Manometer is going to measure the pressure of a gas in a sealed container. And I did go over this in class. I'm going to try to be quick, not go over it here. But again, we know atmospheric pressure here is greater than the pressure in here by a value of H. So the pressure of the gas would be atmospheric pressure minus H. Here we see the atmospheric pressure is less than the pressure of the gas here by a value of H, which means the pressure of the gas is going to be equal to atmospheric pressure plus H. We'll practice a lot in your homework. Pressure and volume, this is one of our first relationships we're going to talk about, and this is Boyle, Robert Boyle's experiment. He was measuring gases here, and then he'd add mercury. right? And so he's describing what happens to the volume of this gas when I increase the pressure on it by adding in some mercury. And what did he find out? Well, he found out when you increase the pressure, well, the gas shrinks, the volume gets less. He ended up making a series of observations, kind of his summation of his data table. What he found out is that this pressure it'd be 48 inches cubed, and then at 35.3, 40 inches cubed. It kept going down as the pressure got higher. Woo, right? That makes pretty much sense. If we look at a graph of that, it's going to look like this, right? And so we have this relationship as pressure increases, as pressure, where am I at? Okay, small pressure, large volume, large pressure, small volume. So as pressure increases, the volume gets smaller and smaller and smaller and smaller and smaller. Okay, pretty straightforward. It gives us a graph. We can solve for it. The graph actually showed V equals K over P, and so we can rederive it, solve for this constant proportionality, and we get PV equals K. Volume pressure are inversely proportional. If one increases, the other will decrease. Again, here's another situation. I had this under 1 atmosphere, now it's under 2 atmosphere, and we've cut the volume in half. Kind of goes along like that, but it is kind of a weird one. So we can set two things equal. P1 V1 equals P2 V2. This happens at constant temperature and constant amount of gas. We can do a real quick practice problem. I taught you guys you need to write this stuff out. And so when I read this, it says you have a gas that is initially at 56 millimeters of mercury. That would be my first pressure. Occupies 1.5 liters. That would be my first volume. If the pressure is increased to 150 millimeters mercury, that's my next pressure. My only unknown in this equation now is V2. I can solve the problem for V2. Charles' Law's experiments, similar thing. He's studying temperature and pressure, and so we have this situation here. He gets this data table, which is kind of cool, right? He ends up deriving absolute zero, and we did talk about this, so I'm just going fast. Again, he redrove absolute zero by extrapolating his data and realized that, hey, the point at which you have zero volume of a gas is negative 273.15 degrees Celsius, so we call that absolute zero. And we have to use Kelvin when we do Charles' Law calculations. If we don't, we're going to run into negative volume. So we do want absolute zero for our temperature, right? So we want a graph that looks like that. So we will deal in Kelvin. Graphs, again, are lines with the equation V equals BT. B is going to be our constant of proportionality that relates volume to temperature, and T is going to be in Kelvin. If we solve this for B, we are going to get V1 over T1 equals B, and then we can set them equal to each other. V1 over T1 equals V2 over T2, so now we can solve problems that are undergoing a system of change. You'll hear me say that a lot. If you have a gas that occupies 10 liters at 150 Kelvin, what is the volume of the gas with temperatures increased to 250 Kelvin? So I've got V1 and T1, and I've got T2. Again, if I go back to this equation, right? All I got to do is plug that stuff in for this equation here, right? This equation here, I just plug those numbers in, I solve for my missing variable, and I move on to the next practice problem. Avogadro's, again, I talked about this. We did some practice problems with this. This just suggests the more gas you put in a balloon, the bigger the balloon gets. It's a mind blower, I know, right? And so here we go. Right, volume and moles are directly proportional. If one increases, the other is going to increase. V equals a constant proportionality times N, your number of moles. Right, again, this happens at constant temperature and pressure. We can, again, set it up as a system of equations here. V1 over N1 equals V2 over N2. I record all my variables in a practice problem so that I remember how to do the math. I know it was quick, you guys. It won't be as quick on the next one since we haven't talked about it yet. But remember, this is all repeat for a lot of you. For those of you who this isn't repeat, please make sure you sign on and ask me some questions later on this afternoon. Again, describe atmospheric pressure and how barometers work. We should be able to do that. right? Identify our units of pressure. We are going to be using those a lot, so please make sure you know those units. I will give them to you so that you don't have to memorize the numbers. Just make sure you know those units. Explain how pressure and volume of a gas are related. We should be able to do that. That was that inverse relationship. Perform calculations using Boyle's law, PV equals PV, right? Describe the concept of absolute zero. It was what Charles derived by looking at how gases change volume with temperature. It's cool. Explain how volume and temperature of a gas are related. Perform calculations with Charles' law. And then again, the more gas you put in a balloon, the larger the balloon gets. You do have a homework assignment. Oh, shoot. Calculating with Avogadro's law. I almost forgot. Yeah, that's we can you can do that. Homework 457, 1 through 7. There's a couple different ways you're going to be able to turn it in. I am going to be typing that stuff up hopefully today into Google Classroom. And then if I don't get the chance to do that, some of you already completed it. All you got to do is take a picture of it, text it to me, make sure your name is highly visible, and we'll call her good. Hey, thanks, folks. Hopefully this whole shindig doesn't take too long. I'd love to get back, hang out with you, do some lab work, that kind of fun stuff. But for the time being, this is how we do things. Okay? Again, assignment due tomorrow. Adios, muchachos. La 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 la.